Right, good evening, ladies and gentlemen. I hope you can hear me. I'm Janusz Adamson, and my talk is about space debris. So space debris is normally associated with artificial materials that orbit the Earth. And the materials can be large as an orbital space station or as small as a chip of paint. But I'd like to broaden the definition to include natural space debris and man-made space debris. Both types of debris can collide with orbiting satellites and interplanetary probes. And this, for example, could cause malfunction or resulting in loss of global communications or positioning systems. So I'm going to start off by saying a little bit about the origins and mitigation of natural space debris, and then say more about the origins and mitigation of man-made debris. So first of all, what is space debris? So we need to start off with stellar nurseries, such as we see here in the Orion Nebula. And for those who don't know where the Orion Nebula is, it's seen in the winter sky in the rising part, so rising in the east. And here I've got a photograph of a protoplanetary disk. So this is how our solar system will have originated, from a planetary disk. The disk the center part would start heating up, which would form the sun. And there are some other images over here these are recent images taken in the last few weeks of a planetary disk and also of star systems in formation. So our solar system is not unique. The planets started by the slow migration of particles from the outer parts to the central parts by means of gravity, and off we go with the planetary system. Now, exoplanets, so we know that there are something like about 4,000 confirmed exoplanets. So like I said before, our solar system's not unique. And the way we know there are other planets orbiting sun-like stars is by looking at the light coming from that star, and we can see that there is dimming, which indicates that there is a planet orbiting around it. Or alternatively, we can look at the spectrum, and we will likewise see a difference in the spectrum, which will indicate that there are planets. So if we look at our solar system, we have the inner planets. We then have an asteroid belt, then the outer planets, which are the gas planets, and further out we have the Kuiper belt and the Oort cloud. So, as you can see by the two images, every single planet apart from Mercury and Venus have got moons orbiting around them, of which I think Jupiter has got something like about 79 moons. Now notice in here I haven't mentioned Pluto, which is a dwarf planet. It originated in the Kuiper belt, which is way past the orbit of Neptune, but its orbit must have been disturbed, and because of that, its orbit is now between the orbits of Uranus and Neptune, and also outside Neptune. Now, we've got some images of objects coming in from the Kuiper belt. For instance, the New Horizons spacecraft has photographed this object here, and this is basically, think of it as two dirty snowballs which have been stuck together, and over time they will either separate or just join up together. This is, I won't pronounce the full name, but its short name is Comet 67, and it was photographed by the Rosetta and the Phoebe probes. Now again, this comet originated in the Kuiper belt, and some objects or stars, for example, like the Schultz star, would have passed through the Oort belt and disturbed its orbit, and we would have had this comet here having now an orbital period of about 7 years. So it moved from something like orbiting around the sun in more than 300 years, once in 300 years, to something like once in every 6 to 7 years. But the disturbance of these orbits isn't just due to stars which may have gone past our sun, but also they can be influenced by our own planets, Jupiter being the largest one. And I don't know if all of you remember, but the comet Shoemaker in, where are we? Which was, I think, in 1996 or thereabouts, when it was orbiting around the sun and it came close to Jupiter, which disturbs its orbit. It caused the comet to break up and then impact into the Jupiter's atmosphere. So this was basically a wake-up call for all of us, because we suddenly realized that the Earth can be bombarded by various types of asteroids and comets of all different sizes, and we need to start taking it seriously. So when we look at our planet Earth, we know there are about 175, or at least 175, impact craters. The famous ones which you probably know about is the Barringer crater in the US, and the one which has recently been in the news, and that is the Chicxulub crater, and the asteroid which hit that part in this area of the US south in the Mexican area, that eventually led to the extinction of the dinosaurs. And the recent modeling has shown that that asteroid came in at a very critical angle, which caused this particular event. If it had come in at a different angle, for all we know, we may not have been here, and the dinosaurs may have evolved to something completely different to what from all the various bones and skeletons that we have of them. Also, the Shoemaker-Levy comet also was an inspiration for disaster movies. Some of you, I'm sure you've seen them, Deep Impact and Armageddon. And what they used in this case was nuclear explosions to try and break up the asteroids. And as we've seen in the film, the consequences of the breakup, that one of the asteroids hit the Earth and caused a great deal of damage. Well, in the other case, well, I can't remember that. I know they just broke it up. Now, just one or two little bits of basic mathematics. First of all, what we need to do is to change the orbit of asteroids which are coming close, which may impact Earth. Now, I don't think nuclear explosion is the answer. I mean, if we just look at some of these very simple calculations, energy is equal to half times the mass and the velocity squared. And if we put some numbers in, like if we were to explode a 10 megaton bomb and put it into the equation, we would be able to shift or change the velocity of the orbit of a 1 kilometer diameter asteroid by about 8.3 meters per second, which isn't very much when that asteroid is probably coming towards us at about 30, 40 kilometers per second. But if we could give this impulse to the asteroid at quite a few astronomical units away, so it's, when we've still got a year, 2, 3 years before it comes and hits us, we would be able to deflect it. We wouldn't really want to use nuclear explosions because we don't fully understand the compositions of all the asteroids and of the comets, and we know that quite a number of them you can think of them as dirty snowballs. So likewise with a ballistic explosion, that's probably not a good idea either. But we are looking at a kinetic impact experiment, or we could use low thrust rocket engines. Problem with rocket engines is that you'll have to crash that rocket engine onto the surface of the asteroid, and then you'll have to have sufficient fuel for the rocket engines to fire and actually move the object from its orbit. But we are doing a test experiment. The launch window for this experiment, it's the NASA DART experiment and the ESA HERA mission. Well, the window is between December this year and June next year, and the DART probe will get to the Didymoon and Didymos system. And I don't think these are the true names, these are probably nicknames, sometime in 2022. The idea is for DART to impact Didymos, Didymoon, because that is the moon which is orbiting around Didymos, and see what is the effect. They hope that they'll be able to give it enough impulse to actually significantly change the orbit of that moon, of Didymoon going around Didymos. And the HERA mission will be close by, observing what has actually happened. So this will, as I said, this mission will start at the end of this year, sometime next year, and will be completed in the middle of 2022. Now, we've also got we have meteorite showers around us, and some of these can actually impact and damage satellites, especially if the satellite is passing through the end or through the actual debris which has been caused by the comets. Now, we know that some of the meteorite showers nearly missed certain aircraft, and we know of at least one person actually being hit by a meteorite shower. So it's moved effectively from objects which are natural space debris, now moving towards now man-made debris. But before I talk about that, one final thing is that space weather can actually affect our satellites. Now, space weather is basically when we have solar flare coming from the sun, and fortunately we are shielded by the Earth's magnetic field, and we see the effects of the solar flare in a form of the aurora display. If we have a satellite which is moving from north to south magnetic pole, then the impulse, the electromagnetic impulse from that solar flare could actually damage the satellite. Fortunately, most of our new satellites going into those types of orbits have got are hardened to electromagnetic pulses. Right, so now we move on to what we understand as space debris, which is man-made debris. And it started with the space age. And the space age, for you remember, was in 1957. But we've had two events before that. In 1926, the American Robert Goddard launched the first liquid propellant. And then during the Second World War, we had quite a few V2 missiles impacting on London. And the V2 rocket in that time could go to a height of over 100 miles. So effectively, the V2 rocket was the first ballistic missile. So the space race started in 1957. Sputnik 1 was the first satellite, the Russian satellite. And the rocket here, which we have here, is really an adaptation of the V2 rocket. The Americans followed fairly soon with the Vanguard satellite. And the Vanguard satellite is still orbiting around the Earth, while Sputnik 1 re-entered quite some time ago. So looking at debris, how does the man-made debris originate? Well, for a start, we need to launch the satellite into orbit. So satellite operations, meaning that the third stage of the rocket, when it separates, will end up orbiting the Earth, unless we've put certain means to deorbit that third stage. And also, when there is a separation, debris will actually spread into space. And that debris is probably just minute types of particles. Now, if a satellite malfunctions for whatever reason and it explodes, that's going to be another cause of debris. Once there is debris in space orbiting around us, then that debris can collide with other satellites, which will further increase the amount of debris. Satellites may fragment, and also in the last few years, we've had several satellites colliding together, further increasing the number of debris particles. And how do we get rid of them? Well, we hope that natural causes, that means the satellites or the debris, will pass through the atmosphere, which will cause the orbits of those particles to get smaller and smaller, and they will eventually burn up. Or alternatively, we need to go to some sort of method of collecting the satellites, retrieving the satellites, and then deorbiting. So right at the bottom, we have, this is the appearance in 1957, and then as we work our way through, you can see more debris in 92 and much more, I think that says 2005. Now, a question we want to know is, how does debris stay in orbit? Which is the same question, why do satellites stay in orbit? Oh, do you want me to carry on? Right, I should carry on. So when we have a satellite orbiting Earth, it's got a velocity of about 7 kilometers per second, but also we have an attractive pull by gravity from the Earth, and the resultant is along this line here, and that is the resultant of those two forces, and that is the path which the satellite makes. And if we carry this on all the time, the satellite will eventually produce a circular or an elliptical orbit around the planet. Now, in order to deorbit the object, we rely on the Earth's atmosphere. The Earth's shape has an effect on the orbit. The moon's gravity will also affect it, and the sun's gravity. Solar pressure, well, that is the continuous nuclear explosions on the sun, and they are sending out streams of particles, and that is the pressure that we're talking about here. And when effectively we're ignoring the orbits of Jupiter, Saturn, Uranus, and Neptune, because they are of an order of 1,000 less than that of the sun and the moon. So looking just at debris, how does it happen? Well, good analogy is a billiard table. There we have, if we hit the ball and we aim it at the number of balls in the center of the billiard table, they will scatter. Now, the little calculation here, that velocity is wrong. The only way to look at that high velocity is when we've actually got a meteorite streaming towards the satellite. It will be moving about 30, 40 kilometers per second. And if the satellite's moving towards it, then the combined velocity could be up to a value of about 84, 85 kilometers per second. And this will increase the velocity by a fraction, basically, by about 0.21 centimeters per second. So a small, very small particle won't have great impact on the satellite, but what it will actually do is to cause scarring on the surface of the satellite. Now, this is what actually happens when you do have a particle or an impact onto the surface of a satellite. And these are actual photographs taken at an MOD site, and the particle is moving in this direction, and when it hits the barrier, that's the surface of the satellite, you can see all the thousands of particles streaming away in the opposite direction to the impact. Or in this case, if it's an oblique angle, which is the more likely type, then the debris will, as it penetrates through the debris here, will actually cause an impact of all the instruments in the satellite, and this is the debris moving away. So in this particular case, we're going to have a catastrophic explosion or complete disintegration of the satellite. In this case, in this one here, we might actually see parts of the satellite surviving. So where were we in 2005? There's quite a few satellites in different types of orbit, ranging low Earth orbit from 200 to about 2,000 kilometers, medium height. And medium height, that is where we have basically our communication satellites, where we get our TV, and quite a few also in geostationary. So the big band along here, that is basically the equatorial, around here, this is where we have the orbit at an inclination. And these satellites, means if we have a low Earth orbit, the orbital period will be about 95, 96 minutes. So if you were out on Saturday seeing Dragon, SpaceX Dragon moving across the sky, it'll have gone across the sky in a space of about 3 or 4 minutes. So all in all, it will have made an orbit around the Earth in about 90 minutes. But if you had an orbit in a geostationary position, 26,000 miles up, it would actually be stationary over the Earth. But if its orbit is inclined, it will actually do this sort of shape here. So that will explain these particles of debris, very high up and very low down. And if we put all the different types of things, you can see how congested it is in space. So looking at some of the observations, now again, I can't see, you may not be able to see all of this very well here, but there are about 22,000 tracked particles, debris objects, and these are more than 10 centimeters in size. In reality, statistically, there's about 34,000. There's about 1 million or so objects between 1 centimeter and 10 centimeter, and about 128 million particles which are less than 1 centimeter. Now, what this graph shows is that it's been a steady increase in time. And then in 2005, if I'm not mistaken, the Chinese sent a missile and destroyed one of their satellites. And as you can see here, these 2,800 or so observable pieces were produced. These are pieces greater than 10 centimeters. And then a couple of years later, we had the collision of 2 satellites, the first ever collision, and since then there have been quite a few more collisions. And this is just again a summary of some of that. So if we could, so with regards to the 2 satellites colliding, this was the collision point, and this is the debris starting to form around the Earth. With regards to the Chinese experiment, this is showing you all the orbits of all the particles, all those 2,000 or so particles orbiting around the Earth. Now, some examples of debris. One of the famous ones is Ed White's glove. Now, Ed White was the first American to orbit in space, and he lost a glove, and they managed to recover it about a month later. Now, other sort of particles which have been in space, there's a spanner which came from work being done on the International Space Station. The space station went and got rid of the refrigerator, but it was put into such a trajectory that it burnt up in the atmosphere after several orbits. But there are also quite a few spent upper stages of rockets, American rockets and Russian rockets. And here's a picture, an artist's impression of an actual satellite explosion. Now, what can this debris do? Normally, if the space station has been hit quite a few times, and this is the size of an impact, this would have been like a flake of paint. And as you can see, it's fairly small. It's only a matter of a centimeter or so across. But if it was a bigger particle, it would have actually penetrated the skin of the ISS. And there have been 1 or 2 incidents where, I think this was a few months ago, there's a report of that particle had penetrated the space station skin and there was a loss of oxygen. So they can be very, very dangerous. Space shuttle has likewise had several incidents. There have been about 80 or so debris incidents, and this is just a picture of one of them. And this one happened, the particle hit the payload door bay. Now, what are the various sizes? We've talked about, the total numbers. Well, the largest space debris was the Skylab space station, which broke up in '79. It was launched by the Saturn V rocket before the orbit as a test. I think, no, sorry, no, I'm getting this wrong. It was launched after the moon orbits, but it was used as a test facility to see how long could people stay in space. And the smallest would obviously be, you're literally flakes of paint. Again, these numbers here go back to about 2005. As we said, the Vanguard one is the oldest piece of space junk. Now, some of you may have seen or you've heard about SpaceX's Starlink satellites. What SpaceX is wanting to do is to establish a super constellation of about 12,000 satellites, miniature satellites, orbiting around the Earth and giving us 24/7 broadband. So that means you'll be seeing these satellites. If you go out in the night sky, you'll see quite a few of these satellites. And if there was one passing overhead, each one would pass overhead every minute or so. Now, this was a photograph of launch of 60 of such communication satellites. If one of them were to fail, then it would be deorbited. Well, that is the plan. And there would be also space satellites in a lower orbit, so that they would be able to raise a satellite from a lower orbit to the actual orbit of the super constellation. Now, with all these number of satellites, this is a huge potential for space debris. Yes, there are protected regions in space where they want to ensure that any satellite in that region is deorbited, because as we've shown from some of the statistics, some of the information, the satellites are starting to crash into each other and the debris is increasing all the time. So we've got basically two safe regions up to the surface, up to the height of about 2,000 kilometers, and also into geostationary orbit. So that's about what I can say about the potential aspect of debris. I should just also mention about the Starlink, that with all those satellites around there, the number of satellites is increasing exponentially in the next few years, and it's going to cause great problems for the astronomers in observing the night sky. Right, moving on to detection methods. We can detect the debris, but they've got to be greater, in this case here, greater than a centimeter at a distance of about 2,000 kilometers. And this is the early warning radar system in Fylingdales in North Yorkshire. And it uses a phased array radar. Basically what it means is that there are a large number of radar dishes. Each one has a signal, and if you can compress the signals together, you can produce one super signal, which has a which can go a long distance and give you a very fine definition. And this is what Fylingdales would see of the Mir space station, which again came down about 20 years ago. The other alternative is to use laser. So if we go and use laser systems, first you need to know where the satellite, roughly where the object is. It's pointless just firing a laser into space, because you're highly unlikely to go and hit it because it's a very narrow beam. But assuming you know where it is, then you'll have a very accurate reading, or the time measurement, from the pulse leaving the station or the observatory to the object and back again. However, there are two things you need to know. You need to know the position of that station to an accuracy of about 1 centimeter or so above the Earth's surface. And how do you get that? By means of geostationary satellites. And you need to know the orbits of those geostationary satellites to the same degree of accuracy. So as we have more geostationary satellites and they take more readings, we are continuously improving the position of our observatories, of our geostationary satellites, so we can get better positions of our debris. But to calculate the orbit of the debris, we need 3 measurements. With 3 measurements, you can calculate the actual orbit of the space debris, likewise the orbit of a satellite if you're following a satellite. Now, we need to reduce the amount of debris in space, so we've got to have some sort of mitigation scenarios. Bottom 2 images here, this shows you that if we carry on as normal, this is the amount of debris that we would get in the number of explosions. If we do take mitigation, if we have mitigation measures, then obviously the number of debris will decrease. And again, if we do the modeling to the year 2025, I think that says 2025, then this, you can see the difference between the modeling or the number of debris on the left-hand side compared to the debris on the right-hand side. Sorry, it's 2055. So obviously we need to introduce mitigation methods to take out initially very large satellites, the dead satellites, because they're going to cause the greatest danger. And then we can start concentrating on some of the smaller debris. Now, this is a slide made in, not by me, made in about 2012, talking about the different types of removal techniques. For very small types of debris, if you know where the debris field is, the best probable way is to either use a laser gun or alternatively some method of sweeping that area, collecting the debris and then dropping it to a lower orbit, and it will then go and burn up in the Earth's atmosphere. In the medium category size 1, space-based laser, the only challenge there is that you can't use a laser when it's cloudy. Or alternatively, when we get to the larger ones, there are several ways in which we can do this. We can either put in a drag device. For instance, we could fire a solar sail behind it, because if we think about the Earth's atmosphere, the larger the cross-section, the greater the drag. Well, the best way to think of it is if you're in a wind tunnel, if you stand sideways, you might be able to walk forward. If you face it face on, you'll be blown over. If you roll up as a ball, you'll definitely be able to crawl through. So by increasing the size of the object, you can actually reduce the orbit, and you can then let the Earth's atmosphere do the rest. You could also do this by attaching a tether. So this would be like a kilometer tether with some sort of object below which will be spinning, and that will reduce some of the momentum of the satellite, and it will therefore start deorbiting it. We could try and capture the satellites and then either bring them to the International Space Station or to go and or deorbit it. But a new idea which has come about is why not charge the operators? Good idea, because somebody will make a lot of money, but then every single operator will have to sign up to this, and then who's going to collect the money? Is it going to be the local government, or is it going to be an international body which will then use that money to create new methods of removing space debris? So one way is to deorbit a satellite, meaning basically is that if you fire its engines at the highest point from the surface of the Earth, so that'll be the apogee point, you will reduce the orbit. That means the next orbit will have a point there slightly closer to the Earth, and the apogee point will be slightly lower down. And if you carry on giving the satellite these impulses in the opposite direction to its motion, the satellite will eventually get into a lower and lower orbit and burn up. If it's a circular orbit that you start off with, then you can actually fire the rockets at any particular point, and it'll eventually burn up. And this is just an example of one such deorbiting application. By doing that, they changed the life period of this satellite from 18 years to, well, actually, it's, to a very, very short period of time. Now, some of the other methods which we briefly talked about is rendezvousing with the satellite, using grabs like this, or if this was the space shuttle, you could have used the extended arm and grabbed the satellite. Or alternatively, if you have a satellite coming close to one of the dead satellites, is firing something to grab hold of it. You will then move on to the next one, do the same thing, attach a tether. So you could actually see that you'll have a satellite pulling a whole number of dead satellites behind it, bring it to something like the International Space Station. That only makes sense because you require less fuel to bring it there, and then let the people on board the space station do the necessary things to actually deorbit those dead satellites. Now, last year there were two experiments. One was to go and put send a net around a dead satellite. And these are just two images of a short video clip. So you can either have one satellite firing a net, or alternatively, you can have three microsatellites, CubeSats, deploying a net and then basically sweeping along and gathering all the space debris or the large satellites. And this is the other experiment which was done, was to fire a dart at this object here. This is a metal plate simulating the outer layer of a satellite, which then penetrates. We have attached is a cable, and this cable will be again attached to a satellite, which will then move that satellite from its orbit to something lower. Or alternatively, at the end of this cable may be a solar sail, which again will start reducing the orbit of the satellite. Now, the idea of the lasers, and we said this is probably the idea of better for the very small particles less than 10 centimeters, is to fire a laser and give it the particle an impulse to lower its orbit, which would eventually go into orbit. Now, Raytheon have actually built a space laser. It's not been deployed or spoken about, basically, because the Chinese, and the Russians were fearful that they could be used to knock out satellites. But there is such a laser in operation. And finally, we can go to electrodynamic tether. Now think of it as a very long rod. This would be carbon fiber graphene, for example, with an object below. And as it is spinning, it is generating a magnetic field, and any metallic particles which come close to this magnetic field will be drawn to this tether. The satellite then would lower its orbit, eject this tether, and all the particles would burn up. So we've mentioned just a few methods which are being experimented on as to how to reduce the number of debris in space. Now, here are one or two rare sites. Recently, there may have been, you've probably seen a photograph last week of a Russian rocket burning up. That's what was seen over Australia, and this is the debris particles. Now, I saw an image, saw this sort of thing in the sky in my teens, but I've never seen anything since then. But that is basically a satellite, in this case a rocket, re-entering the Earth atmosphere, and it's a destructive re-entry. Everything's burnt up. Now, the Columbia Space these shuttles, Columbia, when it burnt up, this was the sort of image that people saw. and on the radar, it was seen as this particular object. So, as we're saying, debris can be very, very destructive. And finally, to finish off, we talked about the International Space Station being in danger. It could be hit by debris particles. Some of you may remember the film Gravity, where the space shuttle, the space station, were totally destroyed, and how you might be able to survive and return to Earth. Well, the space station has got now two modules attached to it, Dragon and also the Soyuz. So if anything were to happen, the astronauts, cosmonauts on board would be able to get into the two space stations and return back to Earth. And in the future, near future, you'll have the US Orion vehicle, which is the vehicle which the Americans are going to use to return to the moon and eventually to Mars. So that's the end of my talk. I hope you enjoyed it. Thank you very much for listening.